Hello everyone, in person and online. Welcome to the Cryosphere Pavilion. Today we have a talk from Dr. Julia Brigham Grady from the University of Massachusetts-Amherst, also a former chair from the US Polar Board. And she will present us a very latest result from an article which presents the risks of massive sea level rise from Antarctica within the Paris Agreement.
Good afternoon and good morning if you're back in the United States listening in. So it's a pleasure to be here, and I'm planning to give you an update on this particular paper that came out quite recently from members of the science community working on what's happening with Antarctica. And over the last 5 years in particular, there have been a number of papers that have come out about talking about what is the vulnerability of Antarctica. So we have to see this as an iterative process where the science community learns more and more and works together and challenges each other to get the equations right in order to understand how the ice sheet behaves. So what I'm going to try to do is summarize some of the work that came out of this paper. My colleague at UMass, Rob DeCanto, is the first author, but there are a number of other authors, Dave Pollard, Richard Alley, and so on, representing a very strong science community who've made a statement with this particular paper. And again, a lot of what I'm going to focus on, and you'll hear this in several talks this week, really has to do with not knowing, not necessarily uncertain, but knowing that there are instabilities in these ice sheets. How do we quantify them? How do we estimate when they can happen? And it has a very big change in the relative impact on global sea level. Antarctica is the elephant in the room in terms of sea level rise. And why is this? The LEADS group this morning reviewed this, and I'll just reiterate a lot of things that the community recognizes, is that around many parts of Antarctica, it's something like 10% of the margin of Antarctica drains 90% of the ice sheet. So a lot, again, 10% of the margin with the ice shelves is draining 90% of the ice sheet. So these ice shelves, these floating ice masses, the ice flows downhill toward the sea, is grounded, and then starts to float. And the end of that floating ice mass can be as much as 400 meters thick. Okay, these are huge, thick ice shelves. And they're floating. But what's happening now, what we're seeing happening more and more is, in fact, warm water from the circumpolar currents, deep water, this warmer water is getting up underneath the shelves. It's melting the base of the ice shelves and also causing the grounding line where the ice shelf meets the ice sheet, causing that grounding line to retreat. And so the warming from the bottom is a concern, but also there are processes going on the top that I'll mention that have to do with what a term we call hydrofracking, which has to do with the strength of water from the surface to actually cause those ice shelves to break up. So a couple of years ago, Rob and Dave Pollard, Rob DeCanto, Dave Pollard put out this paper diagramming this idea of ice cliff instability. And in the top left, they show a different cartoon with the ice shelf extending out, and then with the melt underneath, but with also the fracturing of the surface and then the accumulation of water in these cracks, which then also forces the ice sheet to fall apart. So if these drivers from both the bottom and the top are acting together, it can cause the ice shelves themselves to fall apart. And then the consequences of that are possibly having a cliff. And I've kind of tried to diagram it here, but in the lower left diagram, it's showing 800 meters of ice below sea level and about 90 meters of ice above. So I'm just trying to show it here. Here's the ice cliff, but there's another 800 meters below that. And that high of a cliff is inherently unstable. It cannot hold itself up. And the question is, has this happened before? And it's very hard for us to see this exactly in the paleoclimate record. But modeling and getting this right is really important to understanding the role of Antarctica in sea level rise. So again, going further with their model, just to put it in a little context, we have to remember that these ice shelves draining so much of the Antarctic margin, they really are buttressing the ice. They hold it up. And once you lose the buttress, like in a cathedral, once you lose that buttressing, a cathedral is going to fall, the ice sheets will fall, and you get inherent collapse. So a lot of the debate that's happening is how fast can that happen? What are the major mechanisms? And also in the science community is how do we describe that mathematically in the models to get it as accurate as possible? That's where even 5 years from now, we'll even have it better. The science community will have it better. But what this paper was particularly showing, and it's relevant to Glasgow, is that depending on the top left is plus 1.5 degrees, the middle diagram is 2 degrees C, and the lower one is 3 degrees C. And this is showing you the rate in millimeters of contribution from Antarctica. And just to summarize in the bigger text here, it shows that by 2100, we could have as much as 8 centimeters in a very low emission scenario from Antarctica, which would be great. That's a real minimal number. What's important is also that at 2 degrees, the difference between 1.5 and 2 is only a small amount, at least in these models. But once we get to 3 degrees, it's a much bigger jump in the reaction of Antarctica and how it responds. So there's a huge bifurcation, particularly once we get above 2 degrees. And that's part of the remnants of this. So the paper is showing, for example, here is Antarctica today. The ice shelves are in the lighter blue, and the box is around the Pine Islandthwaites glacier ice sheet, which is retreating quite rapidly. Terry Hughes, years ago, suggested that if the West Antarctic ice sheet was going to fall apart, it was going to get gutted from the Thwaites Pine Island Glacier area, not from the other ice shelves, but from the middle. And it turns out Terry was probably right on that one. So here's a reconstruction of 2100, when in this model scenario, there's a range between 8 and 27 centimeters from Antarctica, but you start to see the demise of the Pine Islandthwaites glacier system. Again, floating ice does not contribute to sea level until you get the grounding line retreat back into the ice sheets. And so that's by 2100. And by 2300, because climate change doesn't stop at 2100, it keeps going. We keep talking about 2100. But it's going to continue. So we have to think farther out. So here we're talking about a range of an average of about 1.5 meters or so, could be as high as 2 meters contributing from these ice shelves as they start to collapse. So an important point for us to think about now, given that we realize that Antarctica, particularly as we approach 3 degrees, anything above 2 is going to accelerate the demise of parts of the ice shelves and parts of Antarctica, is when do we start to do something about CO2? David Attenborough couldn't have said it better. It all comes down to one number. He was brilliant in that statement. Because at some point, what's too much? We already know we're too high. We're at Pliocene levels on CO2 at 414, 15 parts per mil. So we've got to start to pull it down. And what this paper is suggesting is that as we progress up to 2050, is without any change, depending on which pathway we start, when do we start to pull it down? When do we start to decrease CO2? Has a big influence on what happens with these ice sheets. And one of the major outcomes of this paper, a big, strong statement that needs to get our attention, is that if we don't do something and we go as far as into 2060 without doing something about pulling CO2 down, we're going to be getting ourselves on a trajectory where the ice sheet starts to fall apart in a way that we're not going to be able to stop, that it's going to put us on this higher trajectory. Now, if we start by 2060, that's great. But by 2070, all bets are off. We've got a system that more than likely, given what we know now, is going to have a much higher rates of sea level rise. So when we start doing something about it matters, which is why there's urgency for high ambition and decreasing carbon emissions right now here in Glasgow. Now, this paper has some tables, and I'm just going to walk you quickly through them because they're a little complicated, but let me simplify it for you. So the left, this column here, is by 2100. Just to put it in perspective, that's when, so I'll turn 95 in 2050, and Greta Thunberg will be 95 or so by 2100. So just think of it in the person's lifetime, what's happening here. So in the low emissions scenario, Antarctica is contributing a very small amount to sea level rise by 2100. And again, the diagram showed you is at 2 degrees. Again, the amount is still small, relatively small. But once we get to 3 degrees, which is kind of, we're approaching, or at least it's getting better since yesterday, what the agreements are, it's still a lot. It jumps up a lot. And if we just do business as usual, it's quite serious as to how the rate of sea level rise will increase by 2100. Right. Yes. This is so this is 34 centimeters. Right. 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 We don't want that. Yes. Yes. So I think the important point here is that by 2200, after 2100, at business as usual, it really takes off to as much as 5 meters sea level rise. And of course, by 2300, we're up to that number, that second slide I started with this morning, approaching 10 meters by 2300, just from Antarctica. So there's a rapid acceleration of what's happening with these ice sheets once we get anything beyond 2 degrees, which is why staying at 1.5 degrees and maybe imagining going back down to 1 degree, wouldn't that be great? Let's think about that as a new ambition. These two charts also look a little complicated. Let me walk you through them. On the left-hand side is a estimate, particularly down here at the bottom. Whoops, sorry, I'll go back. At the bottom, showing you in blue is with no marine ice cliff instability. So you can do a model of what happens to Antarctica without the instability, or you can do it with the instability enhanced and increasing the rate of sea level rise because of those instabilities, whether you argue for it or not. But you can see that in the low emission scenario, with and without the instability, sea level rise is about the same. Okay, but in the high emission scenario, with and without the ice cliff instability, there's a huge range. So the ice cliff instability still is a very large parameter that needs to be better studied. And we'll be talking more about that later this afternoon. But you can see that anywhere from 12 to 23, it is a huge change in the volume of sea level rise. And so we have big choices with the emission scenarios. And I think the biggest take home from this paper is we've got to start decreasing CO2 quickly in order to avoid a rapid response from Antarctica. And so the science community, a lot of the authors on this paper and others are still working out what are the, how do we best parameterize both the melting of the ice shelves, the hydrofracking from the top, how much of that you put into the models, and then the response of the ice cliff instability to the ice sheets and how rapid that happens. We know that once you remove the ice shelves, for example, when the Larsen B ice shelf collapsed in 2002, we saw that the Crane Glacier behind it rapidly increased by threefold in its outlet. And we see this happening in Greenland and other ice sheets. Once you lose the ice shelves, you get very rapid response, an increase in the rate of flow of the ice shelves behind. So this is an area of active research, and I think I encourage you to take a look at this paper because it really gives you a sense of what is the state of the art that we bring to this to the Glasgow story. And this is an important point that came out of the IPCC report, the AR6, is that for the very first time, and so in the AR5, ice cliff instability was not included. There was nothing about this. This report now includes ice cliff instability, and with the possibility of business as usual and a trajectory of worst case scenario. So what's fascinating for me, I'm not a modeler, but as someone who worries about sea level, the science community recognizes the fact that there still is, even someone who thinks it's less likely, there is still a possibility for that worst case scenario of ice cliff instability taking over the demise of parts of the Antarctic margin. And so the choices we make today are going to decide that trajectory. And I think I'm preaching to the choir here about why it's so important. That's why we're all here in Glasgow these 2 weeks. So with that, I'd like to thank you very much, and I'll try to answer any questions that you may have. Max is going to
the microphone to ask the questions so that the person online could hear them as well. That'd be great. Thank you very much.
Great, thanks.
Hello, my name's. Is this working? Can you hear me? Okay.
Yeah, I can't hear. I can hear you this way.
Okay, I'll speak even louder then. Right. My name's Felix von Geyer. I'm actually a sustainable development journalist. Yeah, actually, the European Space Agency have quite an interesting cube in the green zone, and it shows over 1 trillion tons of ice melt per year. But what I did find interesting is that with the IPCC report, the last one, they're saying that there's basically minimal signs of anthropogenic melting of the Antarctic at this moment in time. And I was speaking to Isabel Lawrence about this, and she said, yeah, actually, the modeling of the Antarctic is, it needs a lot more work. But you're really predicting something quite serious here if we're not doing it. So.
Yeah, so I guess I would challenge the idea that Antarctica is not responding to change. And if you look at the Antarctic Peninsula, you know, Antarctica has that peninsula that sticks up towards South America, that something like 8 of the 10 ice shelves along that peninsula have all collapsed in the last decade or two decades. And in all cases, as those ice, that's the warmest part of Antarctica, and as those ice shelves have disintegrated, you're getting rapid mass loss from parts of the Antarctic Peninsula.
Right.
So remember how big Antarctica is. These various parts of the ice sheet are going to respond differently. So the Antarctic Peninsula is already responding, and we're also seeing the consequences of warm water getting underneath the ice shelves in this region here.
Right. Mm-hmm.
And so to say that human interaction is not impacting Antarctica probably isn't exactly accurate. That's not to say that parts of Antarctica are not warming, but other parts are. And you have to appreciate how large this area is, and how different regions of the continent are going to respond differently to the same climate.
So just to conclude, we could probably say that I mean, the IPCC reports tend to be quite conservative because of the nature of the organization. So it's probably in the political agreement of what should go in that text that they came up with minimizing the damage rather than the actual climate actuality.
Yes, they can be conservative. Pam?
Thank you.
Pam Pearson, ICCI. I actually asked the authors about that when it first came out, and it's simply that there isn't sufficient record on Antarctica of anthropogenic influence. So it's not that we're not seeing it, but it's the record just doesn't go back as far as Greenland. And so that's why they drew that conclusion. I would agree it may not be a very helpful conclusion, but you know, it only goes back, what, really 15, 20 years in terms of the satellite record. So they just felt they couldn't say in the same way that they can for Greenland that you see an anthropogenic influence. But it is losing mass. And they did say that.
But I think that what you said, Pam, is also consistent with the idea that we're being a bit conservative about attribution. You know, people don't want to really commit until it's very solid. But honestly, I think most people would agree that there is influence there that's happening. I mean, because we see these other things, these other parts of the ice sheet are actually responding. So, any other questions? We'll be talking a little bit more later this afternoon about parts of Antarctica and Greenland in other presentations. So we'll go beyond just this paper. Yes.
David Edwards, Open University. Is there any tie-in with what you've been talking about this afternoon with the ice cliff instability and then allowing a speed up of glaciers off the continent into the ocean? Because I gather that a lot of the sea ice acts as a bit of a buttress, a bit of a cork. And if you remove some of the ice at the sea margin, it allows on-land glaciers to speed up, and that's...
Yeah. I think I heard your question. Certainly the sea ice has a role in some buttressing, but it's the ice shelves themselves that are so tremendously thick and are pinned that are really what is the cork, to use your phrase. That's the cork in the bottle. And so as we see more of the margin of Antarctica lose the ice shelves, we're beginning to see acceleration. And this is already happening in parts of Greenland where many of the outlet glaciers, Jakobshavn, Helheim, the Petermann Glacier, where the ice shelves have retreated or collapsed dramatically. We're seeing a huge acceleration. In fact, in Jakobshavn, I teach glacial geology, and I remember 20 years ago, we talked about Jakobshavn, fastest glacier on the planet, moved about 7 kilometers a year. Well, now it's moving at 14, 15 kilometers a year because it's lost its ice shelf. So we're seeing ice cliff instability kind of in a miniature way, call it that, in Greenland. So if you extend the physics and the modeling of that to an Antarctic scale, it makes it seem like a much larger possibility. I just can't emphasize enough how important this is. I mean, when I was a graduate student, I was taught that Greenland and Antarctica were absolutely stable. That's, and so we looked at ice sheet history with the context that these two ice sheets that exist today were stable. We now know that's not true at all. That in fact, both Greenland and Antarctica are extremely vulnerable, and we're pushing the limits on that right now. So, any other questions? Okay.
Thank you very much for your presentation and your questions. Our next event is at 2:30, and we'll talk about the future of Greenland from observation perspective and from paleo perspective. Yep. Thank you very much.
Yep. Thank you.